Welcome to Sita Lakshmi Ramaswamy College. I'm Dr. S. Karthiga from PG and Research Department of Physics. In this session, I'm going to explain you about moment of inertia. Before getting into the technical details, let us see a short story. So this is the story about Preeta, Mithun and Ritul. So Preeta has a sphere and Mithun has a cylinder and Ritul has a hollow cylinder. The three objects are of equal masses and they want to have a race between these three objects. So they wish to see who is the first. So the game started and they can find the Preeta wins the game and the Mithun is second and Ritul is third. So they want to repeat the game again. Again also they can find Preeta wins first and Ritul second, Mithun third. Sorry. Uh, this that is in the game the sphere comes first, the solid cylinder comes second, and Ritul the hollow sphere cylinder comes third. So every time they repeat, they can find the sphere alone comes first and the Preeta wins again. So they want to know the mystery behind it. Actually, the mystery behind it is moment of inertia. Before understanding moment of inertia, which is related with the motion of a body, let us now recall the motion of a rigid body. A rigid body is often defined as one whose size and shape is invariable, so that the distance between any two parts of it is unaltered. So a rigid body can exhibit both translational and rotational motion. So a body is said to be under translation motion if each particle of the body undergoes the same displacement in the same direction in a given interval of time. A body is said to be rotational if each particle of the body rotates about an axis or in a circle. So a rigid body can exhibit either translational motion or rotational motion or both translational and rotational motion. So here the moment of inertia and inertia are related with the opposition that can be seen in the case of translational and rotational motion. The opposition of translational motion is often termed as inertia. The opposition seen in the case of rotational motion is often termed as moment of inertia. So let us see it in now. See them in detail. So before getting into moment of inertia, let us first of all concentrate on inertia. The word inertia actually comes from Latin, which means being idle or sluggish. Actually, the inertia is the resistance or opposition that is experienced by the body in the case of translatory motion. So, or else it can be defined as the inability of a body to change by itself from the state of rest or from the state of uniform motion is often known as inertia, which is also termed as the Newton's first law of motion or principle of inertia. So here the inertia comes from what? You may ask that. The inertia comes from the mass. So the mass of the body is directly related with the inertia. Higher the mass of a body, higher the resistance experienced by the body towards translational motion. Lesser the mass of the body, lesser resistance experience in the case of translatory motion. So you all find a famous example in the case of for inertia. You find famous example in the case of brake. When brake is put on in a bus or car, we feel a jerk. That is because of the inertia of a body. So with this short introduction, we now turn to moment of inertia. Moment of inertia, obviously the opposition observed in the case of rotational motion. So a rigid body rotating about an axis has always a tendency to oppose its state of rotating exactly in the same way as the mass of particle opposes the tendency to its translatory motion. This property of a rotating body is always called as moment of inertia. So the moment of inertia, if the moment of inertia is higher, then the rotational motion motion will experience more opposition. If the moment of inertia is lesser, then we can freely the rotational motion is very free and it can rotate very fastly. So the opposition in the rotational motion is lesser if the moment of inertia is also lesser. So with this understanding about moment of inertia, let us now see the expression for moment of inertia. So as I told earlier, in the case of translatory motion, inertia is related with mass alone. But in the case of rotational motion, inertia, moment of inertia, it is moment of inertia, and it is not only relates with the mass of the body, but also with respect to the distance from, it also related to the distance from the axis of rotation. So here you can find, I have considered, or considered a rigid body which is rotating about an axis O. Here, this rigid body contains many particles. First of all, I consider a particular particle and find the moment of inertia of the particle, which is nothing but mr square. Then I consider the other particles, uh, say their masses be m1, m2, m3, and their distance from this axis is r1, r2, r3, etc. Then the moment of inertia of each particle is also calculated, and then I'm summing all the moment of inertia of all the particles. That gives the moment of inertia of the total object, which is nothing but I is equal to summation over summation m r square. So I is equal to summation m r square. The summation m r square represents the moment of inertia of total object. So, as I have told earlier, so moment of inertia of the total body is the sum of moment of inertia of all the particles, which is summation m r square, and this summation can be simply simplified as capital M in the k square, where capital M is the mass of the complete body, k is the effective distance of its particle from its axis, is often called as radius of gyration. So radius of gyration of a body is often termed as the distance from the axis at which its entire mass m be supposed to be concentrated. So here from the expression of moment of inertia, you can find that the mass of the body is not going to change with the axis of rotation or something else, but the radius of gyration is going to be changed uh, with respect to the position and inclination of the axis and the distribution of mass in the body. So if you consider same object, but if you consider different axis of rotation, then the moment of inertia will change. This is what we observe from here. Also, the moment of inertia, so on the whole, the moment of inertia depends upon the mass, axis of rotation, and also the mass distribution around the axis. So but in the case of inertia, the inertia that is observed in the case of translation motion, it depends only on the mass of the body. But the inertia in the case of rotational motion, that is moment of inertia, depends upon mass, axis of rotation, and mass distribution around the axis. So the larger the moment of inertia, it would be difficult to do rotational motion, or the rotational motion will experience more opposition. The lesser the moment of inertia, the rotational motion will experience lesser opposition. So with this, we come to the original problem. That is, in the story, we have find the sphere comes first, the cylinder comes second, and the hollow cylinder comes third. Now, this is the reason. Here you can find the sphere has moment of inertia 0.4 mr square, cylinder has 0.5 mr square, and hollow cylinder has mr square. So, which is the least one? The moment of inertia of the sphere is the least one. That is why we have the sphere comes first in the ramp, and the cylinder comes second, and as the hollow cylinder has higher moment of inertia, it comes at the last. So as I have told, the moment of inertia is also depends on the distribution of masses. If the mass distributed uniformly about the axis, then the moment of inertia would be less, and if the mass does not distributed uniformly around the axis, the moment of inertia would be higher. A simple example is when you hold a rod and rotate it. So for example, here the boy holds the rod about the center. So if you hold the rod about the center and you try to rotate the rod, you can find it would be easy. But if you hold the rod at the edge and you try to rotate the rod, it would be difficult, because the moment of inertia of the rod about the center about the axis at the center is ml square by 12, and moment of inertia of the rod about its edges is ml square by 3, which is higher than the uh, previous one. That is why we feel uh, rotating about the center is easier compared to the rotating the rod about the edges. I hope with these examples you could easily understand moment of inertia. So as a summary, we have seen about the moment of inertia, which is the opposition seen in the case of rotational motion. So, and inertia is the opposition seen in the case of translational motion. So in the case of translational motion, the inertia depends upon the mass of the object alone. But in the case of rotational motion, the moment of inertia depends on the mass, axis of rotation, and the uh, mass distribution around the axis of rotation. So if the moment of inertia is less, you can do rotational motion fastly. So the lesser opposition is given towards rotational motion. If the moment of inertia is larger amount of opposition is given to rotational motion. So with this, I conclude my talk. Thank you for patience. Thank you for listening. Thank you so much.